Okay, and next we're going to introduce a tool called the projection. And I want to start with looking at the following situation in order to motivate this. So let's say we have a vector u in R2, and we'll label its coordinates with just u1 and u2. Notice that you can do the following. You can write, or decompose is a better word. You can decompose the vector u into the sum of these two vectors here. Right? If the first vector, it has a second coordinate of 0 and a first coordinate of u1, whatever the first coordinate of u is. And then the second vector has a first coordinate of 0, and then the second coordinate is whatever the second coordinate of the vector u was over here. So if you add those two vectors together, you're certainly going to get u. Right? And let's make a couple of observations about this. Just a reminder. Since we're in R2, the standard basis vectors, there's only two of them. There's E1, and it's just going to be, well, you have a 1 in the first coordinate and zeros everywhere else. And there's only two coordinates, so that's what you're going to get for E1. And then E2 is the vector 0, 1, because it has a 1 in the second coordinate and zeros elsewhere. So those are the two standard basis vectors. So what you find is that this first vector that has u1 and a 0, this is exactly equal to u1 times the standard basis vector e1. So that's our first observation, is that this vector u1, 0, it's parallel to the standard basis vector e1. Okay, and the other observation is that the second vector, 0, u2, well, that's equal to u2 times the standard basis vector e2. So we can say that this vector 0, u2 is parallel to the standard basis vector e2. Let's draw a picture of what's going on here. So we'll just draw a sketch. It's nothing mysterious, but it helps to really see what's going on. Just draw a picture here. So let's draw the vector u with initial point at the origin, and then let's say its terminal point is up here. It's easier to draw if you put it up in the first quadrant like that. So this is the vector u. Okay, now if I were to go from this point and look straight down at the x-axis directly below it, well, actually, let me back up. What are the coordinates at this point? If its initial point is the origin, then the coordinates of its terminal point, the terminal point of the vector u, are going to be precisely the coordinates of the vector u. So I can actually label this point as u1, u2. So that tells you that the x-coordinate of this point, as a point in the xy plane, the x-coordinate is u1. So I can label this like that. And the y-coordinate, which is going to be over here, is going to be u2. All right, let's draw these two vectors now. This vector u1, 0, if I draw that starting at the origin, it's going to have a terminal point right here, right on the point on the x-axis, right at the point u1. So this is the first vector. Okay, so that, let me just label it. That is the point, or not, sorry, not the point, the vector u1, 0. And then the second vector, 0, u2, this is a two-dimensional vector. If I draw it so that it starts here, it's going to go straight up and end up at that point. Right, that's what it means for the vector u to be the sum of these two vectors. If you add these two vectors geometrically, you end up getting the vector u, just like that, right? If I first do this first vector and then do the second vector, I end up here, but since I started here, the sum ends up being exactly the vector u. So, but this is the vector 0, u2. So you can see that really what it means to say that this first vector is parallel to e1, it just means it points in the direction of the x-axis. And to say that the second vector is 0, u2 is parallel to the standard basis vector e2, is really just saying that it points exactly in the direction of the y-axis. And we can actually phrase both of these observations without even mentioning the second standard basis vector e2, and we won't be having any less information. By the way, I forgot to draw it, but there would be a right angle there. But we don't even have to mention e2, because this second observation is equivalent to saying that the vector 0, u2 is orthogonal to the standard basis vector e1. So those are the actual observations that I really want you to pay attention to here. Because what we're going to do is generalize this to other settings. But the point is, this decomposition, what were we really doing here? Really, we were just breaking up the vector u into its components, one of which points along the x-axis and one of them points along the y-axis. But there's no reason that we need, there's nothing special about the x and y-axis that allows us to do this. If I were to replace the vector e1 with any other non-zero vector, it turns out I could still do this. I could still build a triangle like this and do a decomposition like this that still satisfies these two conditions. Right, and I'll clarify exactly what I mean by that once we move down and actually state the projection theorem. But let's just read through these two sentences down here, even though I kind of said the rough idea, but let's read through it carefully. So this decomposition is familiar because E1 points in the direction of the x-axis and E2 points in the direction of the y-axis. And by familiar, I mean that we're just breaking up the vector u into its x component and its y component. There's nothing magical about that, right? But what's cool about this is that you can generalize this to other settings where you break it up into components that maybe aren't simply just the x and y components. There's some other they're components in some other coordinate system. So that's the second sense. There's nothing special about the axes that allows us to do this. We can do it with any non-zero vector in place of e1 as long as it's a non-zero vector. Okay. So what do I mean by that exactly? Let's take a look at the projection theorem. So which says the following. We're going to start with two vectors, and this applies to Rn. They don't have to be geometric vectors. So they could be any vectors at all. So u and a are the two vectors we're going to start with, and we're going to explicitly require that a not be a zero vector. Okay, so how should you think of these vectors? Just think of the vector u as the vector that we started with up here. It's a generalization of this vector here that we drew in blue. And the vector a, you should just think of that as the generalization of the standard basis vector e1. So a is playing the role of e1 in this setting up here, but it's going to be the generalization. So we're not going to be as restrictive in this case. So the theorem, the projection theorem, tells you that there is a unique decomposition. U is equal to w1 plus w2. What that means is there's a unique way to choose vectors w1 and w2 such that if you add them up you get u, but also that satisfies a couple of other conditions, which again are going to be the generalization of these two conditions. By the way, the vector w1 and w2, they're the generalizations of these two vectors respectively. So w1 is the generalization of this vector, and w2 is the generalization of this vector. So here, that's why you have u is equal to w1 plus w2 in a sense. That's where this is coming from. Okay, well the two conditions that are guaranteed to be satisfied here is that first of all, this vector w1, it's going to be parallel to a. That's the first condition, really, and it's just the generalization of this statement here. So you can guess probably what the next thing I'm going to write down is. If this is like our w2 and this is our a, we're really just going to say that w2 is orthogonal to a. Okay, so that's really what we're saying. Let's draw the picture of what's happening. It's going to look quite a bit like this picture, but it's going to be more general. I'm not even going to draw the Cartesian plane this time. So let's start with just our vector u. Okay, I'm just drawing any old vector u out in the middle of nowhere. There's nothing special about where it starts or where it ends. It's just some vector u. Okay, and now I'm going to draw a line that goes through the initial point of the vector u. And I'm also going to leave some space to add something else in. So this is our vector L, or pardon me, some line L, and you don't even really need to give it a name if you don't want to. I'm just choosing to because I feel like I should. But this empty space in here, I'm just going to connect this in blue, and I'm going to actually exaggerate the fact that there is a vector here. And this is actually going to be the vector A. So if in the case where L is the x-axis, then you could think of this as just basically the standard basis vector E1. But in general, L need not be the x-axis. But really all we need here is that we have some vector A that happens to point in the direction of L, or more specifically, if you draw A so that its initial point happens to be a point on the line L, well, then its terminal point is also going to be on the line L. But so in problems where you're applying this theorem, I just want to add this in now, the picture may not look exactly like this. It might not be so perfect. In fact, A might be over here, and it might be pointing in the opposite direction, but that's okay as long as it's pointing in the direction of L, in the sense that if you draw its initial point on L, the terminal point will also be on L. Okay, so now what's the point of this? Well, the idea is you can, this W1 and the W2 are guaranteed to exist. So I'm guaranteed, if I go back to where U starts, I can draw now some vector that points in the direction of L, or is parallel to A, right? That's really what this is saying. So here's my W1, and then I also, there's a vector W2 that's orthogonal to A. Okay, so you have a right angle there. Now, I wish I actually, in hindsight, I wish I would have drawn this a little bit further away, because I don't want to give you the impression that that A actually has to be joined onto this triangle at all. That's not the case. They're completely separate. The only important thing about A is that it has to be the direction vector of this line L, in the sense that, again, I'll repeat it one more time, although you're probably sick of me saying it. If the initial point of the vector A is on the line L, well then so is its terminal point. But there's a little bit of space in between the triangle and the vector A as I've drawn it, and that's on purpose, and in fact I wish I had drawn it bigger to really emphasize the fact that this need not be attached to the triangle in any way. In fact, it usually won't be. Okay, so that's the picture you should always have in mind when you're thinking about the projection theorem and when you want to apply it. Now, if I stopped here, this is technically the projection theorem, but the nice thing is you could say more. There's a formula to give you W1 exactly. So that's actually what the rest of this, you can think of this as part of the projection theorem, because they really go hand in hand. So here's a fact. W1 is given by the formula. I'm going to write W1 is equal to, and actually before I write the formula, I'm going to write down some alternative notation for it. We write PROJ, that's just short for projection, and then we write the vector A as a subscript, and then the vector U in brackets afterwards. So some books will omit those brackets. I would encourage you to not copy that. What I would like you to see you guys doing is use those brackets, get in the habit of using them. It just helps you keep everything straight. It's a recipe for confusion to avoid those brackets, especially when you're first practicing with projections. Okay, really, projection onto A, that's how you should read this. This is really a function, and you're plugging the vector U into it. Okay, and the formula, I haven't given the formula yet, it's given as follows. You just take the dot product of U with the vector A, so that's the first part of it, and you're actually going to make a fraction. This is a number, right, because the dot products give you back a number, so that's the numerator of the fraction. The denominator is going to be the dot product of A with itself, and some books will write this as just the norm of A squared. And that's fine too, because that's exactly what the dot product of A with itself is equal to. But this is going to be a scalar. It's a number divided by a number. So this is a scalar, which you're going to put in brackets, and that is you're going to take the scalar product of the vector A. So that is your projection formula. Okay, so that's what gives you the vector W1 in this picture. So if you want this vector W1, just take this vector U and project it onto A using this formula, and then you're going to get this notation really just represents W1. So I'm going to put the box around here, because this is really the takeaway here. The label W1 is just a label. You don't have to call it W1, but if you do call it W1, it'll be given by this formula. So the name, I already said it out loud, but let's write it down. This is called the projection of U onto A. Okay, so that takes care of one of those two vectors, W1 and W2, but that's just W1. What about W2? Well, you can see from this triangle, right, W1 plus W2 is equal to U, or even look over here. If U is equal to W1 plus W2, and if you had U because presumably that's a given in the situation. Let's say you should assume you already know what U is. It's W1 and W2 that you're trying to find. Well, W1 is given by this formula. So if you have W1 given by this formula, just subtract it over to the other side, and you can isolate W2 that way and find it. So that's where this this last note comes from. So it follows immediately that W2 is just equal to U minus W1. And if you'd like, we can put a box around that too, because these two formulas go together. So these two formulas just tell you how to get the decomposition of U that is guaranteed to exist by the projection theorem. Right? You're guaranteed to be able to find W1 and W2. That makes this picture work for any vectors U and A as long as A is non-zero. So these formulas will give it to you. And in fact, you know what? I probably could have just expanded this box to include the W1 as well. So I wish I would have done that, but I can just add it on there now.